I also search for presentations and speakers. So if you're interested in doing a presentation for us, we have a couple of openings for our next meeting in September or later meetings as well. And just as a reminder, our meetings are held on the first Wednesday of each month. Before starting the presentations, I'd like to recognize our top-notch technical team comprised of Andrew and Betty Reed, Emma Seabrook, and Ennio Ciolucci. Thank you for making these online meetings, possible for us. We have 3 presentations this evening, and I expect we will be done around 9:30. The presenters are as follows. Francois Van Heerden will deliver the sky this month. Michael Watson will speak to us about There's No Place Like Home, an astrophotographic tour of the Milky Way. And Ron Macnaughton will talk to us about a web of new technologies and new discoveries. Our president, Tom Luton, will close the meeting with the announcements. And if you have any questions for our speakers, you can enter them in the YouTube chat, and Emma will ask the questions to the speaker on your behalf. And also, if you're attending the meeting for the first time, whether you're a member or not, please let us know through the chat box as well and say hello. So let's get started with the presentations, and Francois with the sky this month.
Thank you very much, Paul. August 2022, there's a number of things that we will be able to see. Of course, I'm going to start with our closest neighbor, the moon. And let's take a look at the lunar phases, the dates thereof, because one of the things will be a big disappointment to you. First quarter happening almost immediately, 2 days from now. So we'll have some additional light to contend with if we're out there trying to observe. Of course, Friday, August the 12th, full moon. It's the Anishinaabe Thimbleberry moon, giving recognition to our First Nations in Ontario. But that also will have an impact on one of the other celestial events that we will want to look at this particular month. August the 19th, of course, is the last quarter, and new moon, when I will be out there doing some extra observing, should it be clear, is the 27th. So get yourself ready for those particular opportunities, especially from Friday, August the 19th through to the 27th. And be sure that you're out there getting whatever observing opportunities you can, and you'll see some of those in a few minutes. So let's take a look at where Mercury is going to be. It's on the 4th. It's visible in the southern hemisphere, and it's challenging for anyone in the mid-northern hemisphere and the latitudes here. In other words, it sucks. To be honest, its greatest elongation on the 27th in the western sky, but it's going to be really hard to see. And from Stellarium, you can see here that Mercury is just this tiny dot that's to the west of the due west, and the moon is in the sky at the same time. Let's take a look at Venus, because that, of course, is always a beautiful object to observe, rising early in the month next to, or very close to, Castor and Pollux. By the month's end, it is 14 degrees from the sun in morning twilight. So this is a good opportunity for you to get out and take a look at it. You can see here where it is. It's really quite close to Castor and Pollux right there in the east, and that will give you a great opportunity to do some photographic work potentially if you are into, or planetary observing. Good opportunity to do it. You can see here it's at 05:27:40 in the morning that I took this from my stellarium. Gives you an opportunity there. The one key thing is it's going to be 4 degrees south of the moon on August the 25th. So this will give you a nice opportunity, if you've got a pair of binoculars, to view the two together in the same field of view. 10 by 50 binoculars tend to give you about a full 5 degrees of view, so that will help getting it all in there. The planet Mars is in conjunction with Uranus on August the 1st. So this would be an opportunity for someone to actually take a look at this. And we have a right angle triangle here for all intents and purposes. You've got the Pleiades here, Mars, and there's the moon. So it makes a nice triangle in the sky for us. Good opportunity for you to be able to get out there to observe that. It's with the last quarter. It's 3 degrees to the north on August the 19th. Again, a nice opportunity for potential photographic work with wide field if you're interested. Jupiter, of course, has 2 double shadow transits. They're both on Tuesdays. So if you're working, it's probably not the best opportunity for you. It's close to the waning gibbous moon on the 2nd, or it's 2 degrees away. It's south August the 15th. So this will give you a great opportunity. And you can see here, it's in Pisces, or very close to it, very close together. Good opportunity for anyone who wants, again, to take a picture, wide angle, even with your cell phone, would be a good opportunity for you. Saturn, the magnitude right now is about plus 0.3, and the rings are tilted 13 degrees, so the north side of it is visible as far as we are looking out there to see it. And it's in Capricorn, so you will have the opportunity to see it. It's 4 degrees south of the moon, August 11th, 12th. So you have this good opportunity once again to find Saturn very easily. The planet's Uranus, it's occulted by the waning gibbous moon on the 18th. Technically, it's visible in Canada, but it's in broad daylight. So fat lot of chance of really being able to get that. But Uranus is actually stationary as of August the 24th, and then begins retrograde motion for 22 weeks. So this will be what you'll be looking at. And we have the Pleiades again, Mars, and oh my Lord, there's Uranus. So this is actually a right angle triangle right here. Good opportunity there to find it easily. You will, of course, need reasonably dark skies. Good pair of binoculars, you'll pick it up fairly easily as long as you're looking in the right place. Again, this is fairly early in the morning, so you're going to have to be up before sunrise to really enjoy it. Neptune rises in the mid-evening and is heading towards its opposition September the 16th. You can see here that it's fairly close to Jupiter. You can see here it was just after midnight, and it's just a tiny dot. Get yourself a good little telescope to have a look at that one. Now we come to why I said earlier that the moon is going to be impacting something. A lot of us love to go out for the Perseids, and the Perseids are going to be August 11th, 12th, and 13th. The 12th and 13th is technically the peak, and full moon is on the 12th. So, of course, another year where you won't see too much, unfortunately. But you can see where the radiant is out of Perseus, just below Cassiopeia there. And I don't recall how many times in the years that I've wanted to go and observe these Perseids and have the moon interfering. It seems like every time I plan on it, that's what happens. For the minor planets, Vesta is actually going to provide a great photographic opportunity. It's at opposition August the 22nd. And for any of you astrophotographers, you should be able to grab some of the Helix Nebula and get Vesta in that same field of view. So that should be something that you might want to consider as a great opportunity. Let's take a look at some potential binocular objects that would be worth observing this month. So I would say to you, August the 19th, of course, last quarter of the moon and the Mars and Pleiades all in the same field of view, roughly. Easily visible in 10 by 50 binoculars. So you'll have this set up right here. And that will be a nice close clustering, as long as you don't mind doing it at 02:30 in the morning. M13, of course, is always spectacular if you go out to observe. And in 10 by 50 binoculars, this is approximately what you will see. And in that same field of view, if you are not in the same field of view, but nearby, if you want to use your binoculars and then jump up to M92, over here in Hercules, that's another option. It will be less spectacular than M13, but still worth going out to observe. The Perseus double cluster. So this is two NGC objects. Well worth going out, not as spectacular, but you'll notice there's M110 and M32. So you're in a very easy to find area. If you find M103, M34, and the Andromeda galaxies, basically, when you're just here, it's just slightly less than halfway. And you just cut up and you can see the two objects there. And that is what the field of view will look like. So you will have the two clusters, the double cluster there, visible for you. I highly recommend doing this. Also worth viewing, of course, in my opinion. I love taking a look at it because there's so much in the southern sky towards the center of our galaxy. And so M11, the wild duck cluster, all-time favorite for me in summer to go and take a look at it. And there's so many other objects. And in 10 by 50 binoculars, the wild duck cluster is in the dead center here. It's not as spectacular, but if you just start scanning around that area, you can see you've got M26, you've got the Sagittarius star cloud, which will stand out if you get to a fairly dark sky site. So that's M24 down here, M16 and 17. It gives you lots of opportunities to go looking at something that is worth getting at. For satellites, what will we actually have? Well, for the next few days, all of the ISS passages are, unfortunately, daylight. The Chinese space station there, that one, you can see here, we've got a couple of really good passes. Again, these are in UTC, so you'll have to just adjust with the time change that we have here. But the brightest one is magnitude 1.1 on August the 6th, and it's a decent height above the horizon. So you've got a couple of them here, three of them that are really well placed if you want to go out and observe that particular satellite. Space launches. So, of course, SpaceX is on its march to being able to launch more rockets this year than ever before in their history. They have a planned launch August the 4th, so basically tomorrow, lunar orbiter designed by Korea Aerospace and the Research Institute to demonstrate lunar solar survey resources and produce a full topographic map of the moon. Their next launch after that, I'm not as thrilled about. Some people will be. August the 9th, some more Starlink satellites going up. So if you're an astrophotographer, those really suck in my opinion, because I get wonderful streaks going through my images. We also have a United Launch Alliance launch that's scheduled for August the 4th, and that one is launching the U.S. Space Force's 6th space-based infrared system and geosynchronous satellite. So if you are one of those individuals that likes to watch the launches, which sometimes I do, it's actually a lot of fun. There are also hopes that the SLS, so NASA's Space Launch System, will actually launch, scheduled August the 29th, for its first test flight with an uncrewed Orion spacecraft. At the same time, they're going to take a bunch of additional things out there. So they hope to go around the moon, orbit it, come back. The capsule will come back and splash down in the Pacific. But they're also going to launch 10 CubeSat rideshare payloads with the Artemis 1 mission. Not to be outdone, there's also Roscosmos. So the Russian Space Federation is planning a launch sometime in August. We're still waiting to see exactly when. And of course, we're very close to the end of what I have for you this evening, but guess who else is planning a launch? India Space Research Organization is looking to launch microsatellites. It's a demo on August the 6th. And as a final launch, there's Electron Lab and Rocket Lab Limited, who are still planning, but they're supposed to be doing this in August. So there you have it, folks. That's what's on tap for this month. Back to you, Paul.
Appreciate you taking the time to present to us. And a great presentation, of course. Do we have any questions for Francois, Emma?
Nope, we actually didn't get any questions.
Wow.
No questions this evening. Okay. All right. So in that case, I guess we'll move on to our next speaker, and that would be Michael Watson. He'll talk to us about There's No Place Like Home, an astrophotographic tour of the Milky Way.
Thank you. And I'll just make sure that that I can be heard. I hope so. Thank you, everybody, for and Paul for inviting me to back to the Toronto Centre to speak about one of my favorite topics. This is a presentation that I made a couple of years ago at the RASC General Assembly, and I have added some new photos and replaced stuff, and so I'm going to take you on a tour. And so I'm going to start by asking, this question: what is home? And so, there are lots of ideas about what home is. Where you go to at the end of your workday. Although during the pandemic, it actually has been, where most people actually have been working. In baseball, it's managing to hit an inside the park or outside the park home run and slide into home base. But for astronomers, what we really talk about and what I like to think about as home is this, and that is our Milky Way galaxy. And this, of course, is similar to a view that we see with our human eyes, which are not very well equipped to detect color at low light levels. I think most people understand that. It's only really the planets, bright stars, and in the case of solar eclipses, for example, the solar the prominences and corona that are bright enough to trigger the cones in our eyes that let us see color. And so basically what we see is gray tone. But when we turn the astrophotographic camera on the heavens, this is what we see. And this is one area, and actually the only one, I think, in which one can truly and properly and accurately say that the camera captures reality better than the human eye can see it. Low level viewing of dim objects at night. And so I call this presentation, borrowing from The Wizard of Oz, There's No Place Like Home. And so what I'm going to be doing is showing you astrophotos that I've taken, all of them between 2015 and 2020. And using this gear. So this is my stuff set up in Algonquin Park. A lot of it that you'll see toward the end of this presentation from the southern sky is me set up in the red outback of Australia, and on various trips over the years. And I should tell you that all of these photos that you're going to see have total exposure times ranging from 5 minutes to 30 minutes in total, with numerous subframes stacked. Most of them are in the 12 to 16 minute range. All of them are taken with a Nikon D810A DSLR. And every time, because I don't have a permanent observatory and I live where I am right now in Midtown Toronto, every time I go out, I have to pack all of this gear in the car. And when I get up to Algonquin Park, set it all up. Or when I get into the outback in Australia, ship it down, take it down with me. I wouldn't do that now. It gets lost between, Pearson and any other airport you're going to, and set it up. So, it's a bit of a challenge. But the fact is that this astrophotography that you're going to see, and some of you have seen it, particularly on my Flickr page, you've seen it before, has to be done from a dark sky site. And that means in Southern Ontario, at least 2 hours out of Toronto. And so moving on then, what does the Milky Way look like? If we were to go away from our Milky Way galaxy and look back at it, what would it look like? Well, we can't send a camera out there, but I think that the best example of that is this, and everybody knows what this is. This is M31, the Great Andromeda Galaxy, with M32 and M110, the satellite galaxies. Now, the Andromeda Galaxy is about 2.5 million light years away from us. It's about 1.5 times the diameter of the Milky Way. And so if we were to go out to the Andromeda Galaxy, which you can't do all the time, you need at least a long weekend to get out there, and turn around and look back at our Milky Way galaxy, you would see something that looks a little bit like this, but probably about 2/3 of the diameter. That would be our Milky Way galaxy. Now, one thing that would be just a little bit different, M31, as we can see in this photograph, is tilted about 12.5 degrees from the horizontal to our line of sight. So it's open just a little bit. If you were to go out there and look back, our Milky Way galaxy is actually tilted about 21.5 degrees, so another 10 degrees. It would appear more open to the observer in the Andromeda galaxy than M31 looks like from here. So let's then go on, and this is one of the oldest photos. This is one of my my early ones with a good DSLR, and this was in 2015, a super wide-angle view of the Milky Way from Perseus up in the upper left to Scutum in the lower right. It's a very, very wide-angle view taken in August of 2015. But what I'm going to do is, in this presentation, start with go from little areas and constellations that we're familiar with. And so we'll start with the northern Milky Way, and in the constellations of Perseus and Cassiopeia. Everybody is familiar with them. Starting around midnight or 1 o'clock in the morning now, you can see them rising in the northeast. They are fall constellations. And so let's take a look at this. And what we're going to be seeing here is an area that is about 135 degrees away from the center of our galaxy. So about a third of the way, where the center of our galaxy is in the constellation of Sagittarius. It's about 1/3 of the way around the sky, around the galaxy from the center. And that's what we're going to be looking at here. And so it will not probably jump out at you what exactly this is, but for those of you who are familiar with my astrophotography, you'll know that I always do labeled versions. So let me show you what this is. We can see here on the right the W, the familiar W, if you can see my cursor, of Cassiopeia. All right, and then we see here what was just being talked about, the double cluster, H and Chi Persei, two NGC objects. This is the constellation of Perseus through here, Andromeda over here, and then this is Cassiopeia. And what I should tell you is that for most of these, I show open clusters of stars as green circles, and then hydrogen alpha red emission nebulae that tend to be pink, well, they are very pink, shown in that color. So just going back then, if we can see here, you can see that there are lots of open clusters of stars. I'll be talking about them again in just a little bit, and some hydrogen gas clouds as well. We tend to get more of them as we get closer to the center of the galaxies. We get down into the Cygnus area, and we'll be seeing those. So this is a really great area. This is a much closer in view than of the double cluster, taken with a 6-inch or 152 millimeter telescope that has a focal length of about 1,250 millimeters in order to get it close in. So that's the double cluster. And this one, again, I believe that this dates from 2015, actually. Nearby is one of my favorite objects, and that is the California Nebula. This one I shot in August of 2019, and this is with my favorite scope, and that, or astrophotographic scope, and that is a TeleVue 660 millimeter focal length lens. It's really great because it gives you a field of view of about 3 degrees by about 2 degrees, and you can get the full object here, the entire California Nebula, in really well. So I really like this this telescope a lot. Let's then go just in a little closer to Cassiopeia. And here what we're seeing again is the familiar W. You can see the double cluster there in the lower left. And they're all this area is absolutely strewn with open clusters of stars, and even a small telescope. They're just gorgeous to see. You are not going to see the colors of the nebulae, but you will be able to see the faint hazy patches of the nebulae that will appear gray, to you. Moving on then, now we're moving in really closer with longer exposures, total exposure times of these objects. This is what's called the Sol Nebula. There are two of these very close by, as we could see from the previous photo. This is the Sol Nebula. Taken in October 2018, and about a year earlier, you will then. This is the Heart Nebula. Now, this is really interesting. Incredible shape to this. I should tell you then, and probably all of you, many of you will know this. All of these objects that show red are what are called emission nebulae, and so this is ionized hydrogen gas that is excited to glow by nearby hot stars. And it is therefore the case that most of these nebulae are associated with young open clusters of stars that emit radiation that then cause the adjacent gas to glow with the characteristic reddish glow of ionized hydrogen. And we see this again and again and again. All right, so this is the Heart Nebula. Okay, and here we see, so you can see actually here, I have shown several of the open clusters of stars that are located, sort of embedded within and associated with this nebula. Let's move on then to another very familiar constellation. We're going actually just a little bit further into the fall and even winter sky. And this is Auriga, one of my favorite constellations. And of course, we have the bright star, and here I'll show it again. We see the bright star Capella, the first magnitude star over in the right side. This is a 50 millimeter lens shot from 2015. And one of the great things about Auriga is this: you don't see hydrogen gas clouds, but there are numerous open clusters of stars, including some of the famous ones in the Messier catalog. And here we can see to show with my cursor, M37, M36, and M38. And there, it's beautiful just to star hop that with a small telescope and see these beautiful glittering open clusters of stars. I'm going to show some closer in views here, but we can see that then in Auriga. So let's then go to, sorry, just get it. Yeah. So we'll go to these. And so this is a photograph then taken. This is actually one photograph taken with a 200 millimeter lens. And I get all three of these objects in here. And what's really interesting, I put all the information there. We can see, how far away they are. They're actually really close by, because the distance from where we are located, about halfway or so from the center of our galaxy to the edge of the Milky Way, from our location to the center of the Milky Way, maybe a third of the way, is about 27,000 light years. These are really close. You can see that these open clusters are in the neighborhood of 4,000 light years away. They're just next door. They're in Mississauga to Torontonians. But you can see also that they're very different in appearance. All of these, M36 is the smallest one there. M37 on the left is probably the most concentrated and the richest, and then M38 on the right side there is really quite spread out and is much larger. And so we see different personalities for all of these, and I really like that a lot. Okay, so moving on. Here then are three closer in views of these three objects that I've just put together in sort of a collage. Okay, so those are the open clusters in Auriga, and these are all then within our Milky Way galaxy. I should also say, and I think you'll probably know this, or you may know this, that open clusters of stars, a couple of things about them. First of all, they're called clusters because they are loosely gravitationally bound together. And as a result, while they do and can dissipate over time so as to become unrecognizable, not in your lifetime or mine, they are gravitationally bound together. But because also they do dissipate over time, it means that any recognizable open star clusters are actually very young, on the order of say 1 to 5 million years of age. After that, they've just dissipated, and you don't recognize them as clusters anymore, as opposed to globular star clusters that have a completely different origin, are very densely packed together, are tightly gravitationally bound to each other, are billions of years old, a good portion of the age of the universe, and can last for billions of years. And we'll see some photographs of those. So then, moving on, we see, and this is all part of the Milky Way and close to the plane of the Milky Way, sometimes outside the plane of the Milky Way, but all part of our own galaxy. We have some very familiar objects. This one, several tens of degrees away, is a similar star cluster in Gemini. I really like this one. We actually, you see here, M35, it's very large, and then another NGC one that I think unfairly doesn't get enough publicity. A really beautiful object there, and we see that. Now this one is further away. You can see this is 12,000 light years away, so almost halfway in a different direction, but almost halfway from where we are to the center of our Milky Way galaxy in distance, although not in direction. And so in the northern Milky Way, we have a lot of very well-known objects, and everybody knows this one. This actually is a fairly short exposure because it's quite bright, taken in September of 2017. The Rosette Nebula in Monoceros, which is further south, taken in March 2017, a winter object. I'm not spending an awful lot of time in this presentation on this part of the sky, mainly because it's too cold to photograph it well, unless you're in the southern hemisphere. But this is the belt and sword of Orion, taken with a 200 mm lens. And of course, we can see here the belt, 3 stars of in the belt, the Zeta Orionis Nebula. And here we see the Horsehead Nebula, and then, of course, the Great Orion Nebula M42. Closing in just a little bit, we can see the Horsehead Nebula there, and then some reflection nebulosity. When you see blue, that indicates reflection rather than emission. It is gas that is reflecting light from a young bluish hot star, as opposed to ionized hydrogen that is fluorescing or emitting light, and that tends to be red. And then the Orion Nebula again. I'm not going to spend a lot of time, as I say, on this. So let's then go now closer down toward Cygnus, and we get to the not quite as well-known constellation of Cepheus. It's large. It doesn't have any really, really bright stars. And what we can see here then is in the lower right, we'll see the North American Nebula in Cygnus, and then this really is Cepheus, what we're seeing, and you'll see a very large hydrogen gas cloud there, which I'm going to take you to right now. And this is one of my, well, we can see here again all sorts of these objects. There are all sorts of open star clusters and these various clouds of gas. This is one of my favorites. This is what's called IC meaning the index catalog, 1386 in Cepheus. It's also sometimes called the Elephant Trunk Nebula, and I think that what you'll see here, if I can show that, you'll see down here the so-called elephant trunk. That's why it's called this. And one of the very noteworthy things about this object, a very large gas, is this one, Herschel's Garnet Star. Now, William Herschel was a great English astronomer, and he observed that this had a very obvious garnet color. The star that causes this gas cloud to emit light and to be visible, this star is 100,000 times brighter than our sun, and is 1,000 times our sun's radius. It's not really known with any degree of precision how far away it is, 3,000 or 5,000 light years. It hasn't really been measured all that well. But this is one of my favorite areas, and it's really fun to photograph as well. So then, moving on, we get to the summer triangle, and everybody knows this. And we know that the summer triangle, consists of the three bright stars Vega and Deneb and Altair. They're very different stars. So here is a photo, 35 millimeter wide angle lens of the summer triangle. And what I'm going to do here is show you then the three bright stars, Vega in the constellation of Lyra, Deneb in the left side, the constellation of Cygnus, the swan, and then Altair in Aquila, the eagle, at the lower right. And so these stars are unmistakable. I should tell you that Vega was the first star that I looked at when I got my first telescope in May of 1970, which is also when I joined the RASC 52 years ago. And we can see also in Cygnus there the stars of the familiar Northern Cross. But in this area, it's staggering how much there is to see. We see various objects that are familiar to us, including the Dumbbell Nebula, which I'll be showing a little bit later. So let's move on. So that's the summer triangle. This is a very wide angle view. But we're now going to go to one of the easiest and most beautiful to observe constellations with a whole host of objects, and that is Cygnus the Swan. And here we see one of the really, really interesting aspects of the Milky Way is that, as we saw with the Andromeda Galaxy, it isn't just one flat plane of stars. There are dust clouds throughout it. And when we see galaxies from afar, we see those dust clouds circulating around, as the galaxy rotates over billions of years. And we can see that as well in our Milky Way. And so here, what we see with all of this dark area here, this is not an area where there's an absence of stars. These are areas, clouds of dark foreground gas that block out the light from stars beyond. This is the great bifurcation or division in two of Cygnus into a much bright area here, and then a fainter area of the Milky Way down here. So this is a standard 50 millimeter photograph. And here what we can see is all of the open clusters of stars and the various gas clouds that are shown so well in astrophotos. But all of the open clusters of stars you can see in moderate telescopes, and they just are absolutely, absolutely gorgeous. So then, right in the middle of and actually, let me just show you, go back here. I'm going to show this area now. Satyr is all of the star known as Gamma Cygni, and in this area you'll see that there's a lot of red hydrogen gas. So let's go forward in that, and we can see a lot of this. Here is Satyr, and here is Deneb. This is a 200 millimeter view. I'm going to then zoom in on it with my better astrophotographic telescope. And here, by the way, we can see that this is the galactic equator. So this is sort of the central axis of the galaxy, and these gas clouds are very close to it. If we get in closer, you can see the star images are much smaller. This is a real astrophotographic telescope that I use for this, which I really just love, as I think you can imagine. And it really is just a gorgeous view. This area, the star, Gamma Cygni right in the middle, and this area of excited hydrogen gas is about 1,800 light years from us. So a lot closer than most of these very familiar open star clusters. And it's about 100 light years across or so. Nearby is a really pretty little nebula, the Crescent Nebula. I find this difficult to photograph. There are a lot of astrophotographers in the society. Blair Macnaughton is one in in Nova Scotia, who produce wonderful, superb photos of this. But with my portable equipment, no permanent observatory, it's a challenge to photograph some of these. And then we get to a very well-known object, and that is the North America Nebula, obviously because of its shape. This is the bright star Deneb. And I should tell you, this is photographed with a 200 millimeter lens. We see the bright star Deneb here, the familiar shape of North America here. Here's the Gulf of Mexico, and here's Baja California and Mexico, and here we see Florida. And I guess we're someplace up right around here. And then its companion, the fainter Pelican Nebula here, with some dark gas clouds in here. This is the northern coal sack, by the way, or part of it. And then you see little other parts of all around here of red nebulosity. So I really like this a lot. It's a great area, and it's not all that difficult to photograph. But we can zoom in then again a little bit more to the North American Nebula and the Pelican Nebula, and they really are beautiful. Again, I just point out, you're not going to see the colors yourself with your eyes, but you absolutely can see the outline, and from a dark sky, the outline of the North American Nebula with your naked eye. And if you have even modest 8x30 binoculars, and that's what I use when I'm out in the field, you can make out the shape of that really easily. And you won't see the color, but that will be an achievement for you. And if you can see that, then you are in a dark sky. All right, and that's where you want to get to. Everybody's going to be familiar with this, not too far away. Actually, sorry, no, I should just tell you then that here, this is a wider angle view, and again, we see the North American Nebula, but this is a great dark nebula called Le Gentil 3, and it's really prominent. You can actually see it as kind of a dark hole in the sky when you're just looking up with your naked eye from a dark site, and astrophotos show it really well. And you can see it's a great big cloud of dark foreground gas, and only the few stars, on this side of it can we see. All the rest of the stars are blocked out by it. Okay. And then everybody is familiar with the Veil or the Cirrus Nebula, again in Cygnus. I really like this a lot. It's also a challenge, I should say, to photograph. It's really fairly large. It's essentially a supernova remnant, and the brighter side here is this side, and I will show you then. That a portion of that, and these are the real colors. Again, you can't see them naked eye, but they are the real colors of this object. So then we are moving along, and we're moving down now closer to the center of the galaxy. You just need to check my time. We're moving closer to the center of the galaxy into Aquila. And actually, I should ask Paul, can you tell me about how much time I have? Because I think I'm not going to have enough time, and I do want to get down to the southern sky. I don't know whether you can give me some kind of indication of how much time I've got left.
Yeah, Michael, you can carry on. There is time tonight.
Okay, all right. Well, that's great, and if you want to yank me, you just let me know. Okay, great, thank you. So Aquila, and this is something that I've been starting to photograph over the last 2 or 3 years. There are so many dark nebulae in this area. This is what's called the Triple Cave, or the E dark nebulae, and yeah, sorry, let me just go back there. And these were all, most of these are numbered with the letter B for E. Barnard, who was an American astronomer in the early 1900s, who made it his business to photograph and to catalog these dark nebulae. And so whenever you see these B numbers, that's what it refers to. Edward Emerson Barnard, born in 1857, died in 1923. And he is best known for the discovery of the large proper motion of Barnard's star, the star that is named after him. And he published his catalog of originally 182 of these objects, later extended to 370 in about 1919. So then we move on to a constellation that is not really very well known, except for 2 things. And this is the constellation of Vulpecula. And the 2 things, well, the first one is fairly well known, and that is Brocchi's cluster. also known as the coat hanger. And let me just point out the various stars here. They're actually fairly bright stars. They're one of them is, well, actually two of them technically of naked eye brightness. But you can see this little asterism or grouping of stars, and you can see it with the naked eye, but it looks really, really great in binoculars. And nearby, then something, and you rarely hear of this actually spoken about when people talk about the coat hanger, is this beautiful the little kind of stardust, super concentrated open cluster of stars, NGC 6802. Brocchi's cluster is actually interesting because for decades until really the late 1990s, it was thought to be an open cluster of stars. That is, loosely gravitationally bound together, as I described earlier with respect to open clusters. But it is now really, it has been demonstrated that it actually is nothing more than a random chance alignment of stars that just happen to be in a coat hanger shape, but they're not really close enough to affect each other and to attract each other gravitationally. So I think that this is kind of an interesting thing, and I didn't know that until until recently. Then we get, of course, to M27, the Great Dumbbell Nebula. This is taken with my larger telescope, the 6-inch refractor, 152 millimeters. Again, that has a focal length of about 1,250 millimeters. Also called the Apple Core, located about 1,270 light years from us, and it is. This is not a supernova remnant. It is the visible remains of a low mass star's expelled gaseous sort of outer envelope. With an X-ray hot white dwarf star in the very center of it, and in this photo you can see stars down to about magnitude 17. So then into Scutum, and we see here we're getting closer to the center of the Milky Way, and we can see that it's starting to bulge out. All spiral galaxies, have thin sort of pancake-like arms, and then these larger central bulges. And the central bulge of our galaxy, of course, is in the constellation of Sagittarius, and from our latitude, it never gets higher than about 20 degrees above the southern horizon, and as a result, we don't get to see it very well, which is why every astronomer, every observational astronomer wants to get into the southern hemisphere, where you see the center of our Milky Way galaxy directly overhead, and the whole galaxy is displayed for us overhead from horizon to horizon. It's just a breathtaking and, frankly, first time somewhat frightening view to see. And so, if you get a chance, absolutely do that. And so here we see various of the smaller constellations here. This is Aquila, and over here Serpens. Scutum is a small is a small constellation here. And by the way, a constellation is not a pattern of stars. A constellation is a defined area of the sky. So when we talk about Ursa Major, well, that's the name of the constellation. But the Big Dipper is not a constellation. It's simply a recognizable pattern of stars within this particular area. Okay, so we then move in a little bit closer, and now we start to see some of these well-known objects. And dead center here, you heard some discussion before about this, M11, the wild duck. I photograph this almost every time when I get a clear sky, and that's this open star cluster here. This one is with a 200 millimeter lens, so it's not all that close. But what you see here is the incredible intricacy. You see all of these are Barnard globules of dark gas. Each one of them has a particular designation, and you see the incredible detail that you can get with a good lens. This is a 200 millimeter Nikkor lens with long exposures, and you see the way I take my photos, they're stopped way down, and so the stars are almost pinpoints, or right to the very edge. The other thing you see here, and I noticed this some years ago, is that you get a distinct color shift from the center of the galaxy, which tends to be more orange yellow, away from the center, which tends to be bluer. And I have seen that. And it's not an effect of altitude. I can tell you that from having photographed it in various locations. So on the left side here, we can see that this is a lot bluer. And on the right side, we're starting to get a lot more orange yellow. And so the color balance really is significant. And here again, you can see all of the Barnard globules that I've labeled here, and various of the open clusters and one globular cluster. But let's then move in a little bit closer. And this then is the wild duck. This is one of my most recent photos. Last year was an almost total wipeout because of weather, but this was in June 2020. This is one of the richest and most compact known of open clusters, almost 3,000 stars. The age is estimated, this is actually fairly old for an open cluster, of about 250 million years. And the reason for that, I think, is that it's not a globular cluster, but it's fairly densely packed together. And so the stars have an immense gravitational effect on each other. It takes a lot longer for it to dissipate into, sort of a lack of, you can't recognize it as an open star cluster anymore. And so here we see, again, I've just labeled it with the various data. I'll just move on. And then we get to the center of the Milky Way in these four constellations. And here we see this, and this is the central bulge of the Milky Way. I'm going to come back to this in just a little bit. This is photographed from the center of Australia back in 2019. And here we see now, and you wouldn't have been able to pick it out because of the richness of the stars. We see the familiar teapot of Sagittarius. I'm going to go back, by the way, to the previous ones, without the lines, and then the tail of the Scorpion with Antares, the first magnitude star in Scorpius here, and then the tail down here. And below, down in this side, this is below our horizon. You can't see it from the northern hemisphere. Our horizon goes about here. All right, and so here we see the teapot of Sagittarius. Let me just go back and see whether you can pick it out at all. Just keep your eyes focused on Sagittarius there. And now you look at it, you couldn't pick that out at all. Now you can with your naked eye. It is a little bit easier, except for the southern hemisphere, because everything is upside down. And boy, is that discombobulating the first time you're south and you're trying to pick out the teapot, and it's apparently upside down. That is really difficult. And what I do is I turn myself like this, looking straight overhead, and suddenly then looking backwards, I can pick it out, and then I turn myself around. Oh, that's what it looks like from the south, because it's just completely different. Okay, center of the Milky Way, and we can see then a little closer in view where the center of our galaxy is, where it's thought to reside, a black hole. One of the great globular star clusters is M22, and in fact, it is the second brightest of all of the globular star clusters. I photographed this this was photographed actually from Australia. You just can't get good enough skies. It was extremely high up, almost straight overhead, so easy to photograph. Here, it's really tricky to photograph because it's so low. This is one of the first globulars to be discovered. It's magnitude 5, so you can see it naked eye, and it's actually fairly close, 8 to 10,000 light years away. So going on, we see now, and these are familiar objects. This is with a 200 millimeter lens. We see the Sagittarius and Serpent star clouds, and these are all going to be very familiar to us, M17 and 16, the Lagoon Nebula M8 and the Trifid Nebula M20 here, with open clusters all over the place, just strewn in this entire area of the sky. And then the great M24 star cloud, which is one of the most unusual objects, maybe the most unusual in the Messier catalog. Here we're in just a little bit closer, again, photographed from Australia. You can see the extreme detail that you can get when you photograph in the southern hemisphere. This is the M24 star cloud, which I really do like. It's very obvious naked eye. I photographed this in June 2020 from here, from Algonquin Park. And then moving on, we then start to see some of these familiar objects, the Omega Nebula M17, which is reasonably well visible from here. This was not one of my best photos. This was early on in 2016. We then move on to the Eagle, what's known as the Eagle Nebula. Now, I should point out that you see in the label here, you see IC 4703 and then M16. IC 4703 is actually the Red Emission Nebula. M16 itself is actually the star cluster in the center of it. And so with the label here, we can see where the star cluster is, and then the very famous pillars of creation photographed famously by Hubble decades ago, which is one of its most famous photographs. This photograph by me is a little less famous, but that's okay. It's fun to be able to photograph something like this. Then we move on to this one I really like. It's sort of turned on its side. North is to the left and south is to the right, because you can get with an appropriate focal length both of these objects, the Lagoon Nebula at the right side, and then the smaller Trifid Nebula at the upper left. Trifid Nebula is really, really interesting because, as you'll see, the actual colors are blue, which indicates, again, a reflection nebula, and the red, which is an emission nebula. And then from the southern hemisphere, when the Lagoon Nebula gets really, really high up, you can get way more of the red nebulosity in a dark sky. And this is one of my favorites because it really shows this object in a way that I find very difficult to photograph here in the northern hemisphere. And we get the tail of the scorpion, and here just a slightly closer in view. One of the really great objects is M7, a very large open cluster, which is really very bright. And this then is the area of Antares and the Rho Ophiuchus Nebula. I've managed to photograph this only once, and I don't know why. This actually comes from September 2015, and this was taken with a 200 millimeter lens. So that's what we can see. And I'm going to finish up here then with a dozen photographs or so, or maybe 20. The southern Milky Way, what we can't see from the north. But it is just the the most exciting part of the Milky Way as far as I'm concerned. Although Cygnus is not too shabby. And here, what we see here, now this is a very wide angle view, and I really want to orient you to this. So I'm going to bring up the labeled version. And what we see here then, if you can see my cursor on the left, Alpha and Beta Centauri. Alpha Centauri is no longer called that. It's called Regal Centaurus and Hadar, very bright stars in the constellation of Centaurus. Here we see Crux, the Southern Cross, way smaller than the Northern Cross in Cygnus, but very obvious. Although I should say as well that to the west there is another cross that's just slightly fainter that rises before that rises before the true Southern Cross. And because people are misled by that, and they see this cross, which is slightly larger, rising first, they think, oh, it's the Southern Cross. No, it's not. The Southern Cross is still below the horizon. This one is called the False Cross because it is visible first. But here what we see is, and you'll see a closer in view of that, we see the Northern Cross, and then over here the Eta Carinae Nebula. One of my, probably the last photo I show in this shot is a closer in view of that. And you will all be familiar with the fact that 2 weeks ago, the operators of the Webb telescope released as one of its photos a small portion of the Eta Carinae Nebula. And so you'll see the fuller thing. And so this is one of my photos that the Webb telescope can't take because it has such a narrow field of view compared with my stuff. Anyway, so this is a wide-angle view of this area of the sky. And here what we see then is the Coalsack closer in, and I think you probably can pick out the stars of the Southern Cross here. they're they're really quite bright. And what we see here, then, this is taken with a 135 millimeter lens, and we can see there the coal sack. This is the again the galactic equator. So this is right on the central axis of our galaxy, with the coal sack and the various open clusters of stars all over the place here. Really beautiful to see. Now, one of the things that I now want to turn to, we saw M22, the globular star cluster. The brightest globular star cluster in the entire sky is this one called 47 Tucanae. And it's not an M object, obviously, because Messier was never in the southern hemisphere and could never see this. It is the brightest one. M22 in Sagittarius is the second brightest, and originally it was mistaken for a star when Ptolemy first saw it, and hence he gave a number 47 in the constellation of Tucana to it. Rather than, for example, it also has an NGC number and so on, but that's why it's called that. This one I find a little difficult to photograph because it's very densely concentrated, and so I had to do a lot of work to so that the center of the globular cluster wouldn't be completely blown out. And what we could see here is that 47 Tucanae is very close to the Small Magellanic Cloud, and I just wanted to show this so that you could actually see, how close they are. This was taken in September 2015 when I was down there with a 200 millimeter lens. We then get to one of the most interesting objects in the entire sky, and I'm getting really quite close to the end now, and that is this one, Omega Centauri. Now you'll notice that in the label here, I do not say globular cluster. It was thought to be a globular cluster until about 20 years ago, when new studies showed that it is the vast likelihood is that it actually is a dwarf galaxy remnant, with most of the galaxy, because it's fairly close to our Milky Way, are very close in fact, only about 15,800 light years away, and it has been blown off. So that's a beautiful one to see. And then finally, last two ones, and actually I'll just go to this one. Here is the Eta Carinae Nebula. This is a photograph I wanted to get for years, and finally managed to get a reasonably decent one in September 2019. Center of the Milky Way, and I will then finish up simply by saying that we then have the Magellanic Clouds, and you can see both of them here. Southern Milky Way, large and small Magellanic Clouds. A little bit closer, the small cloud, and then the large one with the Tarantula Nebula. And that then will finish that up, and all I will say then is this. There's no place like home, and thank you very much. And I hope that wasn't too long, Paul.
No, that was fine for this evening, Michael. Thank you so much. We did have the extra time. Fabulous images, Michael, and of course, always a pleasure to have you speak to us. It's great listening to you. Emma, do we have any questions for Michael?
Yes, we actually have a couple of questions and a couple of comments as well. First comment comes in from Stingray Ray, who says, "Great stuff." Eric Briggs wants to know, he just bought a hydrogen beta filter, which is known for only being for observing the Cocoon Nebula, the Horsehead, and the California Nebula. Will he be able to see anything on other nebulae with it?
Well, yes, I'm going to say yes, and I think probably the question has to do with a visual filter, and not necessarily one that is for astrophotography. That will tend to increase that filter visually will tend to increase the contrast, and so it'll make it a little bit easier. But the problem is, it depends on what you're using it for. In a telescope, you see the North American Nebula just fills the entire field of view of even a rich field telescope, and so the problem is you're not really necessarily going to be able to see it. Because in order to see that you're seeing a nebula, you need to be able to discern the edges of the nebula where it's darker beyond, and then you can say, oh yeah, I'm actually seeing a nebula. And so with larger objects, it makes it very difficult to say, oh yes, I'm actually seeing the nebula. You got to see it smaller and in context is the way I would answer that.
Great, thank you.
Okay.
Paul Markov has a question for you. Which software do you use to process your images, and approximately how much time do you spend processing each image?
Oh, good question. I stack all of my images in a program called Registar, but I use a PC. I don't use a Mac. That's all I've ever used, and I use Photoshop. And I've been using Photoshop for 15 years, and I do all of my processing there. I'm not an expert processor by any means. The entire process to assemble an image, not to do the labeling because that can take 2 hours or more, but just to process the image so that it's sort of acceptable, will take me on the order of 45 minutes to an hour. Sometimes for someone where I really have to, play around, it can take up to 2 hours. So that's approximately it.
Wow, thank you.
Okay.
We got 2 more comments. TQ Michael says, I remember when you used to do this using gas-treated cut 35mm film in a Schmidt camera using very, very long exposures.
Yeah, that's right. I used to have a Schmidt camera, and that was film, and that shows how long I've been around.
And another comment coming in from CDB45, wonderful presentation and pictures.
Well, thank you very much. It was a pleasure sharing them with you, and I hope that it inspires you because yes, I've got some good equipment, but anybody who's prepared to get into a dark sky and spend a little bit of money on just a tracking mount and a decent lens and 35mm camera can produce really memorable photographs. So you can all do it. You can all do it. Okay.
That's great.
Alrighty.
We got another question coming in from Rask Toronto. Have you considered photographing from the top of the Andes, specifically in Colombia? It's at a high altitude and turns into a grassland at parts. It's virtually uninhabited, near the equator, and without light pollution.
Yes, it absolutely is that. I've seen a solar eclipse from the Atacama up there, by the way, but I haven't taken my gear down there. It's very difficult to get it up there. But the other thing is, and the reason I go to Australia is also when we go on our trips, my wife and I, we go to see the southern hemisphere, to go hiking, but also because of all the great wine regions in Australia. And so during the full moon part of it, we're in wine country, the Barossa Valley and so on. And when it gets to be new moon, then we're driving into the outback, and you don't quite get that up in the Atacama. So yes, I've thought about it, and a lot of people do go down there, but I have a marriage to preserve as well.
Great answer. We got another comment coming in from Sue, who says, this was an excellent presentation with clear explanations and beautiful photos. Thank you.
Oh, well, that's very nice. So very kind of you to say that. So thank you for the comment. I do appreciate it.
I've got a question for you.
Sure.
What objects would you recommend to photograph for a beginner?
Well, listen, what I'm going to say is the moon. And I've got presentations on the moon too, and I think I'm known as a bit of a lunar photographer. But if you're talking about the deep sky, where you have to get into a dark sky, first thing is photograph constellations. It's a lot easier, and you can do it with a standard lens, even a 50mm lens with fairly short exposures on a tripod where you don't need a motor-driven clock drive. You can shoot with a 50mm lens up to approximately 20 seconds without getting any noticeable star trailing. And so that's the way to start. And I think that I'll just finish up here. The point about starting off is choose something where you're going to be able to get a good result right off the bat, where you'll say to yourself, I did do the right thing in choosing astronomy as a hobby because I can actually do this myself, and you will be able to do it. So I think that far too often people get into look at all these beautiful photos of the nebulae and so on. And I've been doing this for close to 50 years, and so it takes a lot of time, but you can get good results doing wide angle stuff, which I love, and I still do a lot of wide angle stuff. Not without effort. You need effort, but very early on without a huge amount of time. So that's how I'd answer that.
Thank you.
Okay.
We got 2 more comments. Richard Conway says,
Paul's going to be yanking me off.
Okay, we'll wrap it up. As an Aussie, he can verify the wine is amazing. And Zap Fan says, Chile has wine regions too. So.
That is true. Not up in the Atacama, mind you.
Well, that's it from comments and questions.
Okay,
Thank
great.
you.
All right. Thank you again, Michael. Great having you. We're looking forward to having you on in the future.
Thanks, Paul.
All right, let's move on to our next speaker. That's Ron Macnaughton. Now speak to us about a web of new technologies and discoveries. Take it away, Ron.
Thank you. I've heard Michael talk on many occasions and showing amazing photos, and this might be the only time that somebody shows better photos than he has, for which I claim no credit. Every decade, a group of astronomers get together and they look at the long-term needs for astronomy and what investments they're going to try and wheedle out of governments. And the Webb was one of the recommendations, and it's taken 22 years before it actually has got into the sky, and it almost didn't make it, but I think everybody is quite happy it didn't get canceled. We all have a general idea of what the Webb is. Light comes from, infrared light comes from objects. It bounces off the gold mirrors. It bounces off another mirror, and then something happens to it. I'm going to be explaining. Primary mirror segments sort of go up to chest height of people, and the convex secondary is what's way up there, all covered with gold. And the reason is that gold reflects at infrared wavelengths particularly well, but given that it's soft, they cover it with some silicon dioxide. This is the part that I wondered how it worked and what it was. And I'm going to explain it, but I so wish I went to a place where Webb was to get a picture of me reflected on those mirrors. That must be an incredible thrill. Okay, here's the diagram. The light from the convex secondary mirror is not going straight back. It's actually off axis a little bit. And it goes through to a primary or a tertiary mirror, and then it reflects back, and then it goes in, and I'll explain more detail. So here it's come off axis, reflects off this mirror, which has a weird figure because it undoes all the normal problems with coma, etc., that reflectors are prone to. And then it reflects off a fine steering mirror that is continually adjusting things, and it goes into the focal surface. The tertiary mirror, as I said, has a really weird configuration because it's got to undo all the optical problems, and the fine steering mirror is continually moving. They talked about innovations and in terms of eye surgery, and I emailed Ralph, and he came up with beautiful comments as usual, that it's revolutioned ability to examine eyes with some equipment, probably not what's in the average eye lab, but they can see individual photoreceptors, and it makes laser vision correction more accurate. And I know a few people that had laser vision surgery and had struggles with it, so that's great news. We provided the fine guidance sensor, and this checks the apparent location of guide stars 16 times a second. Then it tweaks the fine steering mirror to keep objects within 6 milliarc seconds. So the accuracy of this is incredible. It also can track solar system objects that move compared to the deep stars, but it's a little less accurate, but it's still quite good. Although I'm only showing the 5 images that they released around July 12th, and they've also done some with planets, but that's not part of this. I'm going to take a little bit of a side trip into the electromagnetic spectrum and the atmosphere. We go from gamma rays to radio waves and beyond, and they all travel at the same speed, same phenomena. The only difference is wavelength, or conversely frequency. Gamma rays can have up to the energy of a ping pong ball that's moving. X-rays and ultraviolet injure us, and that's why our atmosphere is wonderful, except I have a bit of a sunburn in my neck now. And astronauts going to Mars, etc., are going to be exposed to it. I'll get to the visible stretch in a little bit, and then we have infrared below that, and then microwaves, and then radio waves, and the boundaries are all arbitrary. Visible is special for 4 reasons. It happens to be the wavelength of light that the sun emits most of. Second, the atmosphere is reasonably transparent to visible when it's not cloudy, which it too often is. And probably for that reason, our eyes have evolved the ability to see at that wavelength. I think other animals can do, others and not. The fourth thing I'm going to explain in a little bit. But above that is the microwave, and that's the region of wavelengths that the Decadal Committee recommended doing. So I'm going to zoom in on just this narrow area, and Hubble was from 0.1 microns. I convert everything to microns to 1.8, so it goes a little bit into the infrared. Spitzer is further into the far infrared, and Herschel is even farther. The latter two, to cool, needed liquid helium. And when the liquid helium ran out, the telescopes either were completely useless like Herschel, or Spitzer did a little bit of work, but not much. So Webb goes a little bit towards the infrared from Hubble. It can see a little bit of red and orange, but it's mostly infrared. So there are 2 areas. The near infrared is 0.6 to 5 microns, and the acronym is NIRCam. And every time there's a near in an acronym, that's near infrared. This is a camera, and it's just passively cooled to 40 Kelvin. The mid infrared instrument, MIRI, it needs further cooling to 7 Kelvin, and I'll go into more details about that later. So here's a picture of NIRCam. And I'm not going to go into all the details of the incredibly complicated paths that the light follows, but this is a filter wheel. Sorry. And there's an incredible combination of different filters that can be used. And when someone's making a proposal for an observing run, I'm sure they have to explain exactly what it is. And this gives a wavelength. So F150W would be 1.5 microns, and it would be a wide range of wavelengths. And every time you see a picture, say the 12-hour deep sky one that to me is my favorite, they've used several filter wheels and done a few hours for each. And it's going to be quite exciting when they decide to do 2 weeks, just deep sky, but that's still to come. The sensor, actually, they slightly tweaked the ratio for the 2 levels in the near infrared. And here's the image that we've all seen of the planetary nebula. And most of the people that paid for the work live in the northern hemisphere. And almost all of the objects are only visible in Michael Watson's favorite hemisphere. Anyway, this is NIRCam. So the blue or longer wavelength is around 1 micron or something or other, or shorter wavelength, I mean. And the longer wavelength, which is red, goes here. And notice it has a significant expansion. This is actually a stretched spherical object, and just like a clear balloon, you can see easily through the straight part. When you get to the edge where you have a thick layer that you're going through, that's what you see here. And I don't know whether these features are on the top, on the front, or the back. I'm sure there'll be research on it. MIRI is a bigger instrument because it also includes spectrographs and other aspects to it, and it's from the longer wavelengths. When you go longer wavelengths, the photons have less energy. And when the energy of the photons starts getting close to the energy of the thermal vibrations, you get huge noise. So what they have to do for MIRI is to cool it even more. So they not only count on the 5 layers of sun shield that are wider at the outside, so any photons inside reflect and go out, but they also have a cryo cooler, and it has to be on the hot side, the sun side of the things. And it has a system where you have sound in a certain way that cools, and it gets the MIRI detectors down to 7 Kelvin. The other telescopes lost their functionality when the liquid helium ran out. Helium and hydrogen are tiny molecules and can easily escape, and I don't know whether they're going to be able to keep this running for much more than 10 years because it's difficult to keep little molecules from escaping. So here's the MIRI image, and I'm going to show both of them for comparison. The near cam, the blue is 0.6 and the red is 5. And you get all sorts of details. In MIRI, which is the longer wavelengths, now the blue is the shorter of the wavelengths. So what is red here is blue here. And I have no idea why the center here is blue and the center here is red. Now, I've downloaded the full versions of all the files, and I've taken segments of each of these. So this is the biggest version I could find. And in the near cam with the shorter wavelength, you see there's incredible detail here. But in the MIRI, you get less detail, and that's because light tends to bend around objects better when it gets longer, but it also means that the sharpness. And you'll notice that you get the diffraction spikes here in the short wavelength, but relatively few diffraction sites there. And of course, the biggest difference between the two is the star. And here you have 2 stars, and here you have one. Oh, wait a minute. It looks like the second star is on a diffraction grating, but it's so much fainter from the other. The larger, this star would have had a planetary nebula, many millions of years ago. And it's a white dwarf, but the bigger star is 100,000 Kelvin, and it emits mostly in the ultraviolet, and its emissions get less and less as you go further into the infrared. So this is invisible, 250 times brighter than the other star, Mag 10 instead of 16. But when you get into the far infrared, this gets less bright, and the other object gets a little brighter because that's sort of the temperature it is, but I was never able to find the exact temperature. And they get closer in brightness. Now, it also works for planets. If you can take photographs of planets next to stars, the relative brightness of the planets increases, but you also have the reduced resolution by being longer wavelengths, and maybe they'll launch a larger satellite, maybe with 3 Webb telescopes in some sort of structure they build up there. Who knows? But that's an advantage. Now we come to the Carina Nebula, and for many people, this is their favorite image. It's my third choice, actually, if I could rate them. And it's just stunning the way these colors are laid out. And I don't know if NASA hired an artist to pick out the colors, because we can see none of those. They're all infrared and a tiny bit of red at the one end. It's all invisible, so the colors are arbitrary, but this is a stunning image. Notice the little knob here, and now I'm going to show you this image along with the MIRI image together, but you see the MIRI is smaller, so you lose the knob, and the colors aren't quite as impressive when they come with it. But given that it's the longer wavelength, you can see deeper into the clouds. And the comments said that the really red objects are probably stars that have not yet ignited, but they're forming and getting warm. And I picked an area here because that star was exceptionally red. And I heard people talking about it, and they said that this is probably also a star forming. I don't know. And I wonder if some technician left it cheesy in the equipment. I don't know what that is. Maybe 2 galaxies that are merging in a funny way. I couldn't find exactly where on the Carina Nebula this is. This is my best guess. Maybe Michael knows better than I. Notice that in other instruments, they always make north up, but in Webb, perhaps because it's difficult to adjust, they put north in whatever, they orient it in whatever direction it's the system is working. Hubble versus Webb. Given the more infrared, you can see through the dust better. The Hubble, the dust mostly blocked it, and that's one of the many advantages of infrared, as you can see well into clouds. Pink Floyd. I love this album. It separated me and many others from a significant amount of money. And a prism or a grating where they have a series of lines right next to each other at equal spacings separates white light into its colors, as Newton said. And I teach my students red, orange, yellow, green, blue, indigo, violet. Roigabiv is the acronym, and that's the colors of the rainbow. Now, could I ask Andrew to show me on this image, because there's something I want to show once I finish something. It turns out the visible range of wavelengths is a common energy for electron transitions. And in an atom, you can't have any level of the electron. It's got to be either here or here or here. There are different fixed levels it can be. And you can see that by doing what ancients did. They made sacrifices of fatted calves, and they burned them for the gods, or I'm not quite sure why. But the instructions in the Old Testament book in Leviticus are quite specific. You've got to put lots of salt on them. And when the salt burns and the meat, there's a certain level of the sodium atom that the electron is bounced up. And when it falls back down, it gives off a yellow photon. And that's unique for sodium, the pattern. If you do that with lithium salts, you get red. If you do that with copper, you get blue. And these are all unique patterns to the particular ones. They're spectra. And that's the fourth thing that's unique about there. Infrared is a little different because it's lower energy. And I'm going to pretend, I don't know if you can see my image or not, that I'm doing a chicken dance, and my heart is one atom, and there are two atoms on my elbows. And there's sort of a ground state of a molecule. And then if it gets extra energy, it goes at a higher state, but it can't be any state. But eventually it drops back down to ground state, and it gives off a photon of infrared radiation. At the same time, if you have a atom of infrared, at ground state, a molecule at ground state, and a photon of that energy hits it, it suddenly can go. So the molecules can absorb certain wavelengths, and they also can emit depending on the situation. This all happens at infrared. So infrared is so valuable because we can look at molecule transitions and we can identify molecules. This is a probably 50-year-old graph of the spectrum of the different planets, including Earth, taken from a spacecraft. And Venus and Mars have big dips for carbon dioxide where it absorbs things. But Earth also has ozone. Now, the ozone comes because when you have O2 with two oxygens in the atmosphere, some of them turn into O3, and the O3s turn back, so you get a continual balance. And the presence of ozone in the atmosphere means there's oxygen. And where does oxygen come from? Some people say it has to be green plants, and other scientists are now saying, wait a minute, there might be other ways of doing it, but this would be a biomarker. And there's massive research in biosignature gases, and there are different wavelengths in the infrared that show you've got different biomarker gases. And this paper has a number of references from somebody who used to go to Toronto Centre meetings, and this is Sarah Seeger's core expertise. Now, they showed another star that is too far south for us to see, and this WASP 96 is a sun-like star over 1,000 light years away. I could see it with my telescope if it weren't for the Earth. The planet's a little larger than Jupiter, but not that heavy, and it's one of these hot Jupiters that is it orbits only in 3.5 days. It itself is very hot. Now, when a planet transits a star, it blocks some of the sunlight and the brightness goes down. And if this is 100%, it might be hard for you to read, but the bottom is somewhere around 98.5. So it drops about 1.5%. If you have an Earth-sized planet, the drop is a lot less. But the planet blocks all the radiation going through it, but the atmosphere blocks the wavelengths of light that are absorbed by the elements, or the compounds, I mean, in the atmosphere. And they released this by NIRIS, which was made by Canada. And unfortunately, the Canadian experts weren't able to do. There was some technical issue. You can get to the L2 and everything works, but we can't get communication. And this is the graph they produced. So this is the parts per million are blocked. Remember I said it was, 14,000 roughly. And it turns out certain wavelengths are absorbed more than others. And this shows the presence of water and also sand for some reason, and I'm not sure how they did it. Of course, it's not a surprise that water is there, given hydrogen, I think, is the most abundant element, and I think oxygen is 3, something like that. But this way we can find other compounds that might be biomarkers like O3 or methane or others, and Sarah has citations in this paper as well. I've read, but I can't reconfirm, that something like 1/3 of Webb time is going to be monitoring exoplanets. Now, something the NASA is planning is, if you get a device like this with sunflower-like petals, for some reason it causes the light to bend around it to give particularly sharp images of planets. And if you put it 70,000 kilometers away from the observing telescope, you can see it. I don't know whether they're going to use this with Webb or with another, but you'll actually be able to image and measure spectra of planets, and that's coming. And it could be when at Star Party somebody says, "Do you think we're alone?" Instead of saying, "I don't have a clue," or whatever, we're going to be able to say there are experiments that have found enough biomarkers in other planets on other stars that there's life elsewhere. Exciting. Stefan's Quintet. This was taken on a lousy night by a friend of mine, and Hubble took a slightly better version. And there are 5 galaxies that Stefan identified as a group, but the northeast one is 39 million light years away, which is 15 times the distance to Andromeda, and the others are something like 120 times the Andromeda distance away. They get this from the speed, and I'll talk more about Doppler shift later on, but it turns out the whole universe is expanding. That's comes from the Big Bang, and objects that are this sort of distance away are moving faster. And it turns out when you divide the speed by the distance in megaparsecs, you get the Hubble constant. So this divided by that is somewhere around 70, 71. Here's the Webb versions. Notice the near cam, they're relatively smooth. But the MIRI picks up all sorts of details. I don't know if these are star-forming regions in here. This upper galaxy with a very active core, notice the incredible detail that comes out. I have no idea what they are. The MIRI has a smaller space, and they just didn't get the elliptical galaxy down there. That's relatively uninteresting. This is the combined version of the two of them, and I'm just going to zoom in on a couple. Sorry, I'm going to zoom in on a couple. This here shows the part of the galaxy, the nearby galaxy. You can actually see what seem like stars and star-forming regions. And this shows various things of this galaxy that seems to be merging or whatever with the other galaxy. And somebody said you can see an image of the jets that come out, but I can't see anything here, but that's another story. Oh, sorry, I went too far. But there are all sorts of things in this image that might also be of interest, like distance objects. And what they want to do is to be able to get a spectra of a lot. And it's a little bit like the Digital Sloan Sky Survey. It's New Mexico, and they want to take a whole bunch of spectra. So what they do is they get an aluminum sheet that goes right at the focal plane of the camera. And then what they do is drill holes where they know galaxies are going to be, and they stick fiber optics in each of the holes, and then they take a long exposure of that area, and they get a whole bunch of spectra, and that allows future scientists, other astronomers, to say, oh, this has interesting characteristics, let's do further study, and it's made some interesting discoveries. I asked Jim Hesser about this because I didn't know the name of it, and he gave it to me, and also said that at the DAO in Victoria, some astronomers tried to make a device with doors that would open at the galaxies, and Webb has perfected it, and they have a whole bunch of micro shutters that can be opened for something. Unfortunately, some of them are jammed shut, and a few of them are jammed open, which will contaminate nearby things, but that can all be worked around. And here's a field, I'm not sure from which picture, but they have picked a particular thing. So this is like almost 2 arc seconds, and they take the specific spectra of that area and they get individual spectra. They also have something where they break the whole image into pieces with this device, and then they take many spectra at once. Anyway, here's where they took the spectra around the active black hole in the upper galaxy, and this is too hard to see, so I'm zooming in. And I also drew the diagonals, and you can see that this part of the galaxy is moving towards, and this part is moving away with the different ions, and they get this from Doppler shift. And they can find the composition around there. But my favorite image is this one. And this is what Joe and Kamala got to see, along with NASA brass, who obviously want to get more funding. And you've all seen the deep image. I had trouble. I can't find the exact size of the image. And my guess is from a grain of sand at arm's length that it's probably, this is an arc minute. And it turns out they have this galaxy, and it bends light from elsewhere, and you get these Einstein rings. So there's an Einstein ring. There's an Einstein ring. There are 3 Einstein rings in a row here, and maybe others. And what happens is you have a heavy mass and a distant object, and the mass, if it's lined up with where you are, you can get these rings that don't always have the same radius or whatever. It very much depends on it. And sometimes you get a ring that actually magnifies something. And here they found a star that didn't appear in 2011, presumably from Hubble. Yes, it is. And in 2016 it appears, and it could be that it just happened to move enough in the 5 years that it now got magnified by 2,000 times. And my first thought was, well, maybe it's a supernova, but apparently it's kept the same temperature all the time. So it's the same star, and it's 9 billion light years away. That's like 2/3 back to the Big Bang. Who knows what Webb might find? You also have sometimes you get 4 images of the same quasar or object in a row, and these give information on distant objects magnified, but also they can do statistical studies and find foreground masses, and that will help learn about dark energy or dark matter. Now, details, I downloaded the big version that I don't know is 100 meg, something like that. And I decided to pick my 3 Einstein rings. And what I did is I moved the image down, and you've got it at the top. So this is throwing the 3 Einstein rings, except, oops, this looks like an Einstein ring, and it's got a little bend to it, maybe the central object. But this to me looks like a galaxy. And I don't know what this is. I don't know if those are globular clusters. I don't know. I presume it'll come up. And here's a comparison of NIRCam plus MIRI. I couldn't find NIRCam alone, and MIRI only. And it looks like MIRI is a fuzzier image, not showing details. Remember, I said the longer wavelength has less resolution. But the other thing is, I think MIRI, maybe they didn't take as long an exposure because it doesn't show as many things, but maybe it would never show that because the resolution isn't good enough and it's just fuzzy. Who knows? And I just let you look at fully resolved area to what I thought was 3 Einstein rings. Beautiful. The deep image was taken over 12 hours, and my guess is it's a few hours with one filter and a few hours with another. And who knows what Webb is going to discover when they decide to take 2 weeks and just look at the same patch of sky like Hubble did with his deep fields. I talked about the different distances to the Stefan's quintet and the speed. And the speed tells us how far away things are. And I'm getting close to the end by showing you this image of this field, and they picked certain places to take detailed spectra for. And this is too small to see, so I'm going to show you this part in a sec. So you're going to see this in a sec, but I'm going to start with spectrum lines from rest, i.e. the measuring. This is in a lab in Earth, so there's no speed between them. So you have your hydrogen alpha, and it's somewhere around 6.5 to 7, 0.6 to 0.65, something like that. You have your oxygen 3, and Eric talked about is hydrogen beta filter, and you have a line here, and this is what you have at rest. Now, here's that part for the top one, and it looks like because the galaxy we're moving away from the galaxy, or the galaxy's moving away from us. Einstein says relative motion is the only thing that counts. And what you've got here is what the O3 line was 0.5 micron is now almost 2. So the redshift is almost 4. Now, let's look at some of the other ones. This one is 12.6 billion light years away. And the one that was 0.5 is now over 3. So the redshift is like 6. And here it's 4 and a bit, so the redshift is maybe 9. And this one that's 13.1 billion billion years is closer to 10. Who knows what they're going to find when they do the deep field. So what I did is I zoomed in using the large scale on this image, And here's the galaxy, there is there, and the two stars. And I think that is the image of a galaxy 13.1 billion years ago. And that's about 600 million years before the Big Bang. The early universe was very dense because all the mass was concentrated. And they figured there were population 3 stars with just hydrogen, helium, a tiny bit of lithium and beryllium, and no metals. And these are the heavier elements in order in the sun. Because they lacked these elements, huge stars would have formed, and they would have had a short life, and the supernovae would have made metals for future stars. By metals, I mean elements like this. So this is part of how the early universe started. And seeing back in the cosmos, the Hubble can go to about 1 billion years after the Big Bang. Webb so far has gone something like 600 million years after the Big Bang. Maybe they'll be able to go further. I've heard different stories, but nothing that I've confirmed, so I haven't mentioned it. And that will be exciting. So what is we getting out of the Hubble? We're going to learn the Webb. We're going to learn about how stars die and recycle, how stars form, because in infrared you can see through the dust, how galaxies interact, the early history of the universe, and maybe we're going to find the answer to that age-old question, are we alone? Thank you very much.
Thank you very much, Ron, for a very timely presentation, and also for doing all of the research and sharing it with us. Great presentation, Ron. Let's go to questions. Emma, do we have any questions for Ron?
Yes, we have a question. TS asks, why do Einstein rings happen?
Einstein's theory of relativity, general relativity, predicted that the heavy bodies deflect light rays. And in the 1919 eclipse, somebody took a picture of a star next to the sun during an eclipse, and he was able to show the star appeared further away from the sun than it should because the sun had bent the rays. So if you get a big galaxy between us and something more distant, what happens is the galaxy deflects the rays and they come towards us. And sometimes you end up with 4 images like an Einstein cross. And sometimes you get these curves like right there. And a study showed, by the way, that this curve is the same redshift as that one. So it's the same galaxy. I wish I could go further than that to explain it, but it's deflection from something more distant. Okay.
Great. Thanks. Eric Briggs had a comment for you who said, MIRI's cryocooler is a closed system, so it isn't designed to eventually exhaust its coolant, which is new tech.
I completely agree, but it's very difficult to keep helium in something. And I read somewhere that there's worry that in 10 years they might lose some. I agree in theory it's done, but helium's a small molecule and it tends to wheedle out. Anyway, but I agree, Eric, it's supposed to be contained.
You also got a question from TS as well, who asks, how short-lived were those stars?
I'm sorry, which stars is... the population 3 stars?
Yeah.
Nobody's found a population 3 star yet, although there might, maybe yes, maybe no, so they don't really know, but I think they expect them to last just a few million years and then go boom, because they're like 100 times the mass of the sun, because they don't have especially carbon monoxide. The problem is you have a layer of gas and dust, but it's all moving and it can't squeeze closer because the there's the thermal motion of all these things, so it can't get there. So by having carbon monoxide present, it gives off infrared radiation that leaves. It can cool and get bigger, and eventually gravity forces it into one. That's a population 1 star like our sun. The population 3 stars don't have any of that, so they have to get massive before the gravity's enough to pull them together. And I've read that just a few million years, and then they go boom.
Cool. You got a few comments from CDB45 who says, interesting presentation, thank you. Serge Roy also says, excellent presentation. And Zapfan says, looking into the period of reionization. And Sue also says, thank you for your outstanding research.
Okay.
And that's all the questions and comments we got tonight.
Thank you. And there's talk here, I guess I didn't show reionization. And I wish I knew more about cosmology to explain it. You notice I was kind of waving my hands at that stage of the talk because I'm not there. Well, thank you very much. It's really exciting to watch what Hubble's producing. I just want to show one cartoon where the wife is saying that James Webb Space Telescope is showing us images of 13 billion light years away, practically beginning of the universe. Doesn't it make you ponder the miracle of our existence? And her husband says, we're out of beer. Anyway, who knows what's going to happen. So thanks very much, everybody. Bye-bye.
Thank you very much, Ron, again. And of course, thanks to all our speakers for this evening, Francois, Michael, and Ron. So that concludes the speakers lineup for tonight. Let's move to Tom Luton with the announcements. And Tom, before you start, I want to let you know there's a couple of questions for you.
All right.
And Emma, do you want to tackle those questions?
Sure thing. So the question comes in from Richard Conway, who says he's interested in joining and would love to attend an event first, if that's possible. Could you recommend a meetup where they can learn more and start observing?
I absolutely can. Actually, the simplest answer to that question is for me to go through the announcements, because I'll be talking about things like what's coming up in terms of events, and also talk a little bit about how to get a membership. So was that the only question, or are there any others?
Nope, that's it. That's the
All
only
right, so I'll answer the question by going through the announcements. So hi everybody. My name's Tom. I'm the club president. I'm speaking to you from downtown Toronto, and want to thank you, especially those folks here in Southern Ontario who are joining us on this stormy evening. Let's just get into the announcements. First up, from the 2020 Royal Astronomical Society of Canada's awards have been announced and released, and I am delighted to announce that Toronto Centre member Chris Vaughan has won the Simon Newcomb Award for Excellence in Astronomical Writing. Just going to quickly read off the citation. Chris Vaughan is known as the Astro-Geo guy, since he's also an Earth scientist. Aside from his hard work at the Toronto Centre, where he's an operator and tour guide for the David Dunlop 74-inch telescope, he is also the co-creator and presenter in their Skylab Planetarium. In between his public outreach appearances, he writes a weekly astronomy news bulletin called Astronomy Skylights that is geared toward non-astronomers. In this newsletter, he not only points out what's in the sky, he also explains things in an easy-to-understand manner and educates his readers, who can be found in all parts of the world. As well, Mr. Vaughan has been writing for Space.com since 2016, and he is also a regular contributor to Sky News magazine. His content is also used in the very popular app Starwalk 2, as well as the Starry Night software package. And most recently, Chris co-authored 110 Things to See with a Telescope, together with RASC member John Reed of the Halifax Center. So once again, congratulations to Chris Vaughan, winner of the 2022 Simon Newcomb Award. So just to repeat what Paul was saying earlier, welcome to those of you joining us online. This is one of two types of meetings we have online. You've just witnessed one of our recreational astronomy nights, and starting up in September, we will be having our Speakers Night series. Excuse me. Please use the YouTube chat if you're joining us live. Say hello, enter a few questions. If you're a new member, introduce yourself, and you're coming from far, far away, please let us know where you're coming from. Our next recreational astronomy night is on the 7th of September, 7:30 p.m. Claudio Oriani will be talking about the sky this month, and as Paul mentioned earlier, we've got 2 open spots. If you've got something you'd like to present, please drop a line to Paul. Coming up the DDO in the next few weeks, on Saturday, August the 6th, from 9 p.m. to 10:30 p.m., Margaret Ekape will be discussing probing the epoch of reionization with the Simmons Observatory. There's a $12.76 fee, but registration is online and the links can be found at raskto.ca. On Sunday, August the 7th, 12:30 p.m. to 1 p.m. is Sunday Sun Gazing. $6.92 fee. Again, registration online. On Saturday, August the 13th at 9 p.m., we have DDO Up in the Sky, the Perseids special, co-hosted with the Alan Carswell Observatory at York University. $12.76 fee. And registration online links at raskto.ca. And rounding out the DDO program for the month of August, Sunday, August the 14th, 11 a.m. to 12 p.m., Ask an Astronomer with Chris Vaughn. This one has a $5.65 fee, and registration, again, the links can be found at raskto.ca. So, we reopened our outreach as of April 1st. Our public outreach, and just a quick reminder that we recommend that volunteers and visitors wear masks. We recommend telescope operators disinfect their eyepieces, focus knobs, and any other touch points like step ladders with a 70% rubbing alcohol following each visitor family unit. We require visitors to disinfect their hands before touching any information booth literature. And when deciding whether or not you want to participate in the outdoor events, all members, please consider your personal health and comfort first. So, coming up at Millennium Square, we've got a public stargazing event on this Friday, August the 5th, 7 p.m. to 11 p.m. And then our next one is September 2nd. That's the Friday before our next recreational astronomy night. So join us and our sponsor, Durham Skies, for an evening of free public stargazing along the North Shore of Lake Ontario at Millennium Square in Pickering. Observe the moon, stars through our telescopes. Check out the literature at our booth and ask us some questions. If you bring your own telescope, we'll be happy to help you set it up and aim it at the moon. Just a reminder that the temperature down by the lake can be cooler than you might expect. Please check our website for go no-go decision based on the weather before heading out to the square. And if you're a Toronto Center member, we are still looking for some volunteer assistance with the upcoming Millennium Square this Friday. So please drop a note on the forum if you're able to help out. So City Star Party observing sessions have already restarted. We've had 2 successful ones. The most recent one being just last night. Our next City Star Party, therefore, is the first clear night of the week of September 5th to 8th. Dark Sky Star Parties details are still being worked out. City Star Party is at Bayview Village Park, which is located excuse me, on Bayview, just north of Shepherd. The Carr Astronomical Observatory in Blue Mountain is open. Access to CAO facilities by members and families are only in a modified communal fashion, with total site occupancy limited to 25 individuals. I may not have made this perfectly clear the last time around. So the upstairs washrooms for upstairs bookings only. The maximum occupancy for the upstairs bedrooms is 2 people from the same family per bedroom for a total of 6 people staying upstairs. Communal areas are limited to 3 people wearing masks. All CAO users can use both kitchens, the downstairs washroom, and the downstairs washroom with masks. Full details are on the website. Please read everything before making your bookings. So, the RASC Toronto Centre runs on volunteers, and we're looking for a few folks to fill some empty chairs. We are still looking for a light pollution committee chair. We're looking for a volunteer committee chair. We're looking for a marketing committee chair and some members to fill out the marketing committee. The AV committee, the folks who work so hard, so many times a year to put on these wonderful online presentations, are really looking for some additional assistance. Education public outreach are looking for additional help, especially online presenters, and as well anyone who has the necessary camera gear who can be a telescope camera operator for virtual star parties. Just a reminder that to volunteer, you must be a member first. Contact myself at president@rascto.ca if you'd like to help out. Now, RASC membership. You can renew or sign up online at secure.rasc.ca. Just a reminder that for long-time members, there is a RASC emergency fund if things aren't going so well. It's completely confidential. Gift memberships are also available. For those with additional questions after reading the website, full details can be found by emailing the national office at mempub@rasc.ca. And with that, I would like to wish you all a very good night. I want to thank you very much for joining us here online. Please follow us on all the forms of social media we've got listed here. If you like what you've seen here on YouTube, please like and subscribe and hit the notification bell. Be safe and keep looking up. Good night, everyone.